Okay, in this session we will talk about Z transforms. We will discuss their importance and how Z transforms are calculated for different sequence of signals. At the end of this session, we will be able to identify how to calculate the Z transforms of various signals. We will be able to identify the region of convergence, and we will also look at the solutions for various common signals and what are the equivalent Z transforms. So, let us start now. Earlier we have seen Laplace transforms, and now we are seeing Z transforms in this session. Basically, Laplace transforms are applicable for continuous time signals. If a signal is discrete, then we apply Z transforms for this. So, that is the basic difference between a Laplace transform calculation and a Z transform calculation. Let us see this. Continuous time analysis, as I have told, is a Laplace and Fourier transforms are used. As for discrete time signals and systems, we use Z transforms. The advantage of using a Z transform is that when I apply this Z transform to a difference equation, we will get a simple algebraic equation for that. Z transforms provide a means of characterizing an LTI system and its response to various signals by its pole 0 locations. So, as you see here, Z transforms basically are used for discrete time signals, and when a differential equation is given and apply a Z transform to it, I will get a simple algebraic equation which is easily solvable. And also, when I want to characterize a particular system, an LTI system, then when I apply a Z transform to it, I will be able to find out the response of the system in terms of poles and zeros. That is the main advantage of using Z transforms. Let us see the concept. What is the concept? The Z transform of a discrete time signal x of n is defined as the power series x of z given by summation of n is equal to minus infinity plus infinity x of n z to the power of n. This is for all those values of z for which the x of z converges. This equation, as you see here, the summation is from minus infinity to plus infinity, is bilateral, extending from left hand side and also to the right hand side of the axis. It is extending from minus infinity to 0 and 0 to plus infinity. So, it is a bilateral Z transform. Also, we can have a unilateral Z transform. Let us see this on the board. Okay. So, Z transform is applicable to a discrete time signal. So, you have x of n here, and then when I calculate Z transform of this, we use the letter x of z. Okay. So, x of z actually tells us what is the notation used for calculating the Z transform of a signal x of n, which is discrete in time. Now, how do I get this? X of z is when I take the Z transform of x of n. So, this is how it is, and there are two types. What are they? One is bilateral Z transform, okay, bilateral Z transform. Bilateral Z transform means it is a summation from the minus infinity to 0 and 0 to infinity. Okay. So, if I have an axis like this, so this is 0. So, somewhere here you have minus infinity and somewhere plus infinity here. If it extends on both sides, this is called as a bilateral Z transform. What is the formula for that? So, how to calculate x of z? X of z is given by z of x of n, that is summation of n is equal to minus infinity to plus infinity. That is a sequence which is existing from minus infinity to plus infinity. So, the summation of that n is from minus infinity to plus infinity, x of n, okay, z to the power of minus n. So, this is the equation for a bilateral Z transform. So, similarly, I can have a unilateral or one sided. This is also called as double sided. We can also have a unilateral or one sided function. So, how do I get that for that? For that Z transform, as you have guessed it correctly, x of z is equal to summation will now one sided. So, it is from 0 to infinity. So, n is equal to 0 to plus infinity x of n z of minus n. Okay. So, these are the basically two types of Z transforms. One is a bilateral or two sided, the other one is unilateral or a one sided Z transform. So, when I look at this Z transform, if the summation is extending from minus infinity to plus infinity, this is the formula. x of n z to the power. It is called as a two-sided. Now, single-sided means what? N is equal to 0 to infinity, x of z, z to the power of minus n. So, these two flavors of your z transform you must be aware of. Depending upon the type of equation given, to identify whether the system that is given to us is extending from minus to plus infinity or is extending only on one side 0 to infinity. So, this is how we have to calculate the z transform. Let us see the advantages of z transforms. What are the advantages if I apply a z transform to it? One, the first advantage is differential equations of a system are converted into simple linear algebraic equations. That means if the differential equation is given, the solution sometimes may be difficult. So, what we do is we apply z transform to it, we will get a simple linear algebraic equations which can be solved very easily. Okay, that is the first advantage of a z transform. Let us see the second advantage. The convolution in time domain is converted into multiplication in z domain. So, when I convolve two signals in time domain, when I calculate the z transform for it, it will be a simple product. That is, instead of convolving in time domain, if I multiply them in the z domain, it will be same as convolution in time domain. Third point, almost all signals are converted into z domain which are not possible in discrete time Fourier transform. Okay. So, what happens is in almost all signals I can convert into z transforms. When we look at an equivalent of this z transform, it is called as a discrete time Fourier transform. Here all signals are not possible to be converted into discrete time Fourier transforms. So, z transforms comes in to that place where almost all signals can be converted into z transforms. I read this again, third one, almost all signals are converted to z domain which is not possible in discrete time Fourier transform. Let us look at what is the region of convergence. Okay. The range of values of z for which x of z converges is called the region of convergence or ROC of x of z. That is, it has a finite value. So, the summation which we do, summation of n is equal to minus into infinity, x of n z to the power of n must be less than infinite. Then there is, it converges. So, there is an ROC that exists for that type of z transforms. Okay. The region of convergence is that. Let us see the properties of region of convergence. Also, set of values of z or the set of points in z plane for which x of z converges is called ROC of x of z. That means the set of values of z or the set of points in z plane for which x of z converges is called as ROC of x of z. So, ROC region of convergence, as we solve some problems, we will be able to get calculate ROC for also for various signals for which z transform exists. Let us see the properties of ROC. The first property of ROC is the ROC or the region of convergence of x of z consists of a ring, the z plane, centered about the origin, only a ring and sometimes a disk. That means the ROC of a x of z. If you see the ROC of Laplace transform earlier, it is a lines parallelly which are parallel to the y axis, isn't it? That's in the case of a Laplace transform. Whereas in the case of a z transform, they are circles or disks. So, let's just see on the board how does an ROC look like. Okay, let us take this. Okay, this is my real axis and this is my imaginary axis. So, the ROC is, this is origin, ROC will be like this. Okay, let us just draw this. This is the ROC. Okay, this is the imaginary plane and this is the real plane and this is the our z plane. Okay, you see here the ROC is in the form of a ring or a disk. This is the circle, okay, of a certain radius, let us say some radius here. So, this is the ROC. Generally, it's looked like this. The second property of ROC. The ROC or the region of convergence does not contain any poles. This is very important. The region of convergence of a Z transform does not contain any poles. Okay, that's the second point. Third, if x of n is of infinite duration, when the region of convergence is the entire Z plane except possibly at Z is equal to 0 and or Z is equal to infinity. So, if x of n is infinite duration, this is what is the ROC for the entire z plane, except possibly at z is equal to 0 or and z is equal to infinity. Now, let us say if x of n is a right sided sequence and the circle of mod z is R naught is in the ROC, then all finite values of z for which z mod z is greater than R naught will also be in the ROC. Okay, that means if you have an x of n which is an right sided sequence of having a certain radius R naught, then the region of convergence will be all the z plane beyond R naught. Okay, so let us just see this. Okay, now let us see how the ROC exists for this. Okay, this is my imaginary axis, this is my real axis, this is the z plane. Okay, and this is the, let us say this is R naught for us. Okay, so region of convergence will be, okay, you can just put it here clear. So, this is my, this is the ROC, okay, in the case of a right handed sequence. Let us see the next property of ROC. If x of n is a left sided sequence and the circle mod z is equal to R naught is in the ROC, then all finite values of z for which z lies between 0 and R naught will also be in the ROC. This is the case of a left handed sequence. Let us see this. Okay, again let us see how does it exist for a left handed sequence. This is for a left handed sequence. Okay, this is my imaginary plane, this is my real plane, this is my z plane. Okay, let us draw a circle. This is R naught and this is 0. Now, in this case the ROC is completely this. Okay, so this is the region of convergence for such a left handed sequence. Next property. If x of n is a two sided sequence and the circle mod z is equal to R naught is in the ROC, then the ROC consists of a ring in the z plane which includes the circle mod z is equal to R naught. Okay, now we have seen left handed sequence, we have seen right handed sequence, and if it is two sided sequence of x of n, then how does the ROC, where does the ROC exist? As given here, the ROC consists of a ring in the z plane which includes the circle mod z is equal to R naught. Let us see this. Okay, this is for a two sided sequence. Okay, this is for a two sided sequence. So, let us draw this again. Let us take the, this is the z plane, okay, consisting of real and imaginary axis, and then this is 0. Then the ROC will be like this. Okay. So, this is the region of convergence in the case of a two sided sequence. Let us see some properties of Z transforms now. We have seen the properties of an ROC. Now, we will try to see what are the different properties of Z transforms, starting from the famous linearity or superposition property. We will start now. Okay. Let us see the first property. First property is known as linearity or superposition property. So, here if x1 of n is a sequence, is having a Z transform x1 of z, and similarly x2 of n is a sequence which is having a Z transform x2 of z. Okay. The first one is having an ROC which is equal to R1, the second is having an ROC which is equal to R2. Then if I add these two, then what happens? Okay, we will scale and then add. So, let us see this. A x1 of n plus b x2 of n will have a Z transform which is a x1 of z plus b x2 of z, and the ROC is the intersection of R1 and R2. Let us see this. Okay, let us see the first property, property number 1. Okay. So, let us take an x1 of n, this is one series sequence, this is having a Z transform which is x1 of z. So, we will write here z. So, that means we are transforming to S. This is one series, and let us say this is having an ROC which is equal to R1. Similarly, let us take another sequence which is x2 of n, okay, having a z transform which is x2 of z. Okay, let us say this is having an ROC of region of convergence R2. Now, according to this property which is called as linearity or superposition property, if this x1 of n is scaled by a factor a, that is a x1 of n, okay, then x2 is scaled by a factor b, then if I add these two, they will have a z transform which is equal to, what is z transform of this? X1 of f, we have taken it as x1 of z. So, that will be again equal to a x1 of z plus b x2 of z. Okay, this is what is linearity superposition. Now, what will be the ROC of this? The ROC will be intersection of these two. Okay. So, this is the linearity or superposition property. Let us see the property number 2. It is also called as time shifting or translation property. Now, what does this time shifting or translation property say? Z of x of n is scaled by a factor plus or minus k, then that will be equal to z plus or minus k to the power of plus or minus k x of z. This is the time shifting or translation property. Let us see this. Here z transform of x of n earlier, x of n, now this sequence is scaled. Let us say scaled by plus or minus k, okay, time scaling. Then this will have a z transform, x will have a z transform of x of z obviously, okay, and then this will be scaled by a factor z plus or minus k. So, this is the time scaling property. X of n or plus or minus k in the time domain will have an equivalent z transform which is z to the power of plus or minus k x of z. This is called as time scaling or translation property. Let us see property number 3. It is called as a frequency shifting property. Z of e to the power of j omega n x of n is equal to x of e to the power of minus j omega z. That is the frequency shifting property. Okay. So, that means if x of n is shifted by a certain frequency parameter e to the power of j omega n, its equivalent will be x of e to the power of minus j omega z. Okay, let us write this on the board. So, let us say this is my e to the power of j omega n x of n. This will have, as per property frequency, this is frequency shifting property. So, this will be equal to e to the power of minus j omega z. So, this is the frequency shifting property of z transforms. Let us look at the next property, that is property number 4, which is called a scale change property. Z of, that means the z transform of sequence x of n multiplied by a to the power of n will be equal to, will have a z transform, that is x of z by a, and if x of n is scaled by factor a to the power of minus n, then it will be x of az. This is called as a scaling property. So, what does it say? Z of a to the power of n, x of n is equal to x of z by a, and z of a to the power of minus n, x of n is x of az. So, let us see this on the board. So, this is property number 4. Property number 4. Okay. We all have this. X of n is having a z transform x of z. So, z of a to the power of n, x of n will have a z transform which is equal to x of z by a. That is the property. Similarly, if this is a to the power of minus n, x of n, then this will be equal to x of az. This is called as the time scaling, this is, I repeat, this is called as scaling property. A to the power of n, z by a, a to the power of minus n az. Let us see the next property called as time reversal property. Property number 5 is called as a time reversal property. Z of x of minus n is equal to x of 1 by z, that is the time reversal property. Then again we have the famous convolution property in Z transforms, that is given as follows. So, the convolution, that is Z of summation k is equal to minus infinity plus infinity, h of k, x of n minus k will have a product of h of z and x of z. This is the convolution property. When I convolve in a sequence, that is h of k convolved with x of n minus k, and summation is from k is equal to minus into plus infinity. As I take z transform of this, that will be equal to h of k, that is h of z, that is the z transform of it, and x of n having a z transform x of z. So, this will be a product of h of z and x of z. Let us see the seventh property, it is called as a differentiation property. So, z of nx of n is equal to minus z d by dz of x of z. So, this is the differentiation property, that is z of n of x of n is equal to minus z d by dz of x of z. This is called as the differentiation property, and is property number 7. Let us see the next property, property number 8. It is also called as integration or accumulation property. Integration or accumulation property. What does it say? X of n divided by n plus a, if I take a z transform, that will be equal to minus z to the power of a integral 0 to z, z of minus a minus 1 x of z dz. This is called as integration, also called as accumulation property. So, what does it say? It says the z transform of x of n by n plus a will have is equal to minus z to the power of a integral 0 to z, z to the power of minus a minus 1 x of z dz, that is integration or accumulation property. Let us look at the initial value theorem, which happens to be the property number 9. So, what does it say? So, having said that x of n is having a z transform x of z, so initial value theorem is as follows. N tends to 0, that is x of n, that will be x of 0, that is the initial value, is equal to limit z tends to infinity x of z. So, n is tending towards 0, then its z transform limit z will tends to infinity x of z. This is called as initial value theorem, that is x of 0 is given by or is equal to limit z tends to infinity x of z. Next property. The next property is of course the final value theorem. What does it say? X of n is having a z transform x of z. X of n is having a z transform x of z. Then x of infinity, that is limit n tends to infinity x of n, that is equal to x of infinity is equal to limit z tends to 1 minus z to the power of minus 1 x of z. This is the final value theorem. So, x of infinity will be equal to limit z tends to 1 minus z to the power of minus 1 x of z. This is the final value theorem. This is the final value theorem. If there exists a z transform, there must also exist a inverse z transform. So, what is inverse z transform? Inverse z transform is the process of obtaining the discrete time sequence x of n from the given x of z, that is, it is a process of transforming the z domain into the time domain. So, what happens? You have a x of n, you calculate z transform, you will get x of z. Now, given x of z, I want to calculate what is a sequence, time sequence x of n, then that process of converting a z transform into a sequence, that is x of n, is called as inverse z transform. Let us see the various methods to calculate the inverse z transform. The methods are as follows. The first one is called as the inversion integral method. The second one is the convolution theorem method. Third is the long division method. And the fourth one, the most popular one, is the partial fraction expansion method. All these methods are used to calculate the inverse z transform based on the type of equation given. Okay, during the course of this session, we will see, given a z transform, how to calculate the inverse z transforms using various methods available, and which one is the more apt for us to calculate the z transform. Now, let us look at how a z transform can be used in the system function calculation. Suppose let us say I want to find out what is the stability of a given system. If I apply a Z transform to it, how will I be able to find out whether the system is stable or not, as an example. Okay, let us start this. Okay, let us take a definition H of Z. H of Z is defined as follows. So what is H of Z? It is consisting of a numerator which is a summation of m is equal to 0 to capital M, Bm Z of minus m divided by a summation of terms k is equal to 0 to n ak z to the power of minus k. System is having an input x of z and the output is y of z, and the system function is h of z. Then the output will be the product of the input and the system function, that is y of z will be equal to x of z and h of z. Let us see this on the board. Let us take a function here. Let us take a system here. Let us say this system is having a system functionality as h of z. The input, okay, input is x of z, okay, then the output, this is y of z. Then y of z will be equal to x of z and h of z. Okay. So the output is a function of the input x of z and also the system function h of z. The function h of z is called the transfer function of the system, or is also called as system function. We have used system function as one word. It is also called as the transfer function, which is the famous word h of z. Okay. So if x of n is equal to delta of n, the unit impulse sequence, then x of z is equal to 1. Apply a sequence delta of n, then x of z will be 1. Therefore, what is y of z? Y of z is h of z multiplied by 1, that is x of z. Then y of z will be equal to h of z. Okay, and h of z is a z transform of the impulse response. That is, if I want to calculate what is h of z, h of z is calculated easily when I know the sequence h of n. So z transform h of n will give me the h of z. Okay, h of z is stable if the poles of h of z are all inside the unit circle mod z is equal to 1. So if I know h of z and if I can calculate the poles and where they are lying, if the poles are all inside the unit circle mod z is equal to 1, then the system is stable. This is how we try to calculate the system functions. So if I know h of z, if I make x of n is equal to delta of n, apply to it, then x of z will be equal to 1. When I apply this to a system, h of z will be equal to y of z, and if I calculate the poles of the function, and if all the poles lie inside the unit circle, that is mod z is equal to 1, then the system is said to be stable. So h of z is giving lot of information. We can calculate the stability of a system if I know what is the h of z for such a system.